Welcome to another episode of PG Radio. On this episode of my podcast, I have the prodigal physicist Roy Brener with me. Roy has previously been associated with the Imperial College of London, if I'm not wrong. Correct me when I'm wrong. He is currently involved with the Atlas experiment at CERN Large Hadron Collider in Geneva. He's also been part of T2K experiment in Japan along the same lines, and now is a graduate student in experimental high energy physics, am I right? At Technion, Israel Institute of Technology. Did I get all of that bang on?
This is correct, and let me say I'm pleased to be here. Thank you for having me on the
It's
program.
entirely my pleasure, man. Thank you so much. You have made quite a journey from Israel to New York. What do you think about New York?
Well, it's one of the greatest cities, of course. I haven't been here for 15 years.
Mm-hmm.
I'm greatly enjoying it.
Mm-hmm.
I forgot how fun it is.
Right.
It's my first time at Columbia University,
Mm-hmm.
which is spectacular,
Mm-hmm.
just from first glance. My brother has been a student here for 3 years, so
Mm-hmm.
it was about time I visited the university.
Right.
So far, New York is very
He's
nice,
been treating you nice.
immensely.
Does Columbia have like a lot of weight in the physics world? Is there a lot of dope?
Yes,
Yeah.
yes, of course. So Columbia University is definitely one of the greatest places to be in physics.
Uh-huh.
Both, I wouldn't know about all fields in physics, but especially I can say for theoretical high energy physics, definitely people like Brian Greene and other people who have been affiliated. I think John von Neumann was affiliated at some point with Columbia, and many others, Nobel laureates, and their high energy experimental high energy physics group is very good. It's also involved in the Atlas experiment at CERN as I am.
Right. Wow. Okay.
So yes, it's a very good place to be in. I know some graduates of Columbia University who I work with at CERN. So yes, of course,
All right.
I'm very
nice.
very excited to be here. Definitely.
I'd always assumed the Ivy Leagues were phenomenal for social sciences, but I did not know they were as good for natural sciences. But let me ask you something, because it's always interested me. I remember I was a little boy when this entire episode with the Large Hadron Collider in Geneva was happening, and whatnot and XYZ. I was probably 13, 14, something like that. What exactly goes on? What is a Large Hadron Collider? What are we trying to do there?
Well, okay, so let's decompose the name, of course. So large, meaning it's extremely large. The diameter is 27 kilometers. It's well over 100 meters underground. It's the most energetic. It's the biggest, the greatest, and so on. It encapsulates area that goes through both Switzerland and France. So that's the large bit. Well, hadrons are composite particles made out of two or more quarks. We can talk about later a bit what's a quark, but generally speaking, it's hadrons are particles that are composed of subatomic particles, which we currently do not know to decompose. So quarks, we think that quarks are building blocks themselves. The Greeks thought that atoms are
The building blocks.
the building blocks themselves,
Right.
and that's why the name atom affiliated to Greek as fundamental or unbreakable. So quarks are perhaps now what we think of the candidate to be the atom or unbreakable that the Greeks thought. Anyway, quarks are components of hadrons, and hadrons have two or more quarks, like a proton and so on. So Large Hadron Collider. Collider means collider, so meaning it collides hadrons.
Right.
So what goes on is that this is an accelerator that accelerates particles, composite particles like hadrons, bangs them into each other, and then investigates the outcomes of the collisions in different experiments, different detectors. The detectors are extremely large and are there to record the energy, momentum, and other properties of particles that are results, that comprise results of such collisions. So this is the Large Hadron Colliders, essentially an extremely big laboratory divided up to different experiments, roughly speaking 10 experiments, which every one of which is a big international collaboration, has got sometimes thousands of people from dozens of countries around the world, dozens of universities. So for example, Atlas, the one I am involved in currently, is the largest experiment with the largest detector and indeed the largest amount of collaborators.
So is there, in this acceleration process, in this collision process, are they aiming for a fission or a fusion outcome? What are they aiming for?
Well, it is not necessarily a fission or a fusion. Fission and fusion are natural processes that happen in nature that we know how to invoke.
Right.
Although we need not invoke them ourselves, we can use radioactive materials in which we have particle fission.
Right.
And of course, we can observe fusion in the sun.
Right.
What people have been trying to do over nearly 20 years is manage to have sustainable fusion power.
Right.
Fission and fusion are not exactly the opposite processes, but not too far off being the opposite of each other. Although they are processes behind which the physics is quite agreed upon and quite understandable.
Right.
The challenge of, well, we can talk about nuclear energy,
right,
but generally speaking, just to separate this from high energy particle physics, so nuclear physics and nuclear power currently, I would say, comprise more of an engineering challenge,
applied science kind of
challenge
thing.
And applied science indeed, than investigative science and big questions of reality. So we know how fission works. Fission is known, and you can see, for example, in France, it's a country where fission power is, I think, comprises over 50% of the total power.
Wow. I had no idea.
Yes, and well, we had an unfortunate case with Japan in Fukushima.
Right.
But this, until then, served as a good example of sustainable fission power. And I do hope that fusion in the near future will be achieved, perhaps by the JET laboratory near Oxford, in Oxfordshire, and perhaps by another collaboration in France.
Right.
But this is not what we do in the LHC. In the LHC, we are smashing protons into each other. Protons are hadrons, composite particles. Protons comprise the building block of the atom. It stands in the center of the atom. It's positively charged. It's very heavy. So we take protons, smash them into each other, and then try to see with the
what happens,
smart detectors, what goes on after that. This is not a fission nor a fusion reaction per se. It's just smash, then different reactions, and then we see what goes on.
So do we know what we are expecting from this smashing? Because I remember when this experiment was to be done, there was this paranoia about, like the first experiment was to be done, there was this paranoia about probably creating a black hole, or that there was this hope about finding out how the Big Bang happened, and what we discovered was the Higgs boson, which we term friendlily as the God particle. So do we have an idea as to the fuck are we expecting from this, or do we not?
This is a good question. Every experimental endeavor is supported by a good amount of work which is called phenomenology. Sorry,
Phenomenology.
It's a very long word.
I know.
Phenomenological
Yes.
theoretical work. Phenomenological theoretical work.
Let's practice that one more time.
In phenomenological high energy physics work, which is in some sense theoretical,
Right.
but in another sense it's well correlated with the experiment, because the phenomenologists are trying to probe what more or less can be found, and they are in charge of providing theoretical models that may be tested with the apparatus at hand in the LHC.
Right.
So, for example, for the Higgs you mentioned, the Higgs theory has been supported by theoretical work essentially since the 60s. So if one examines the work of such figures like Peter Higgs and Francois Anglet and even the late Tom Kibble of Imperial College, about the Higgs,
Right.
we can trace back years after years and decades that they've done good work in completing the Standard Model with the Higgs boson, the Higgs mechanism, the method through which masses are given to particles, in a sense, how the Higgs field works as a mass provider. And of course, when the LHC started, people were hopeful that the Higgs will be found, and indeed it was found shortly after. So to your question, yes, when we're investing a lot of money, lots of manpower, lots of time, which of course can be translated to money, take a lot of risks internationally, lots of universities involved, this is usually backed up by good theoretical work,
Right.
not to shoot out in the dark. The theoretical work is often specific, so we have an idea of a range of energies that, and maybe a range of what we call branching ratios. Branching ratios describe the ratios of different decay modes or decay processes of particles. So if a particle decays, it can decay, let's say, to A, B, and C. So the probability decays to A can be described by its branching ratio or branching fraction. So yes, we have a good idea before we start. So if we are looking for dark matter, for example, which is very popular, there would be solid theoretical work about dark matter in certain decay channels and candidates of dark matter particles.
Right.
Yes.
So why exactly? And we did go over it a little before when we were talking, but I think not a lot of people understand what Higgs boson is, at least the layman, given the significance of what Higgs boson is and the fact that this experiment, like you said, is a collaborative effort almost for the good of the world entire. So let's get it clear before we move on. What exactly is the Higgs boson? Why is it called the God particle?
Well, it depends who call it the God particle. But
the newspapers.
Yes, I don't call it the God particle. I don't know many physicists who do. But of course, the Higgs boson is the last part of the puzzle that has been the main puzzle of high energy physics in the 20th century, which is the Standard Model, which describes all the particles we know in nature today to a very high accuracy. Bosons, generally speaking, are force carriers. The Standard Model describes 3 of the 4 forces known in universe. Strong,
weak, electromagnetic.
Weak, and electromagnetism.
Right.
The force of gravity is not described by the Standard Model. Now, bosons are force carriers. So, for example, a photon, the light particle, is a boson which carries the electromagnetic force. Similarly, W, Z bosons are carriers of the weak force. And indeed, gluons are the carrier of the strong force. So the Higgs is a boson, and it's not exactly a carrier of one of the forces. That's why it's so special. It's a generator of a field called the Higgs field. And through that Higgs field, the all particles which have mass, and even a photon which is massless, their masses can be understood via the Higgs field generated by the Higgs boson.
Wouldn't that fit into the picture of gravity with like general relativity and whatnot?
That's a very, very good question.
I'm impressed by myself.
Yes, we don't know. Regarding the Big Bang, of course, before the Higgs was discovered towards the summer of 2012, people were afraid because the LHC started. It was the first time that it was such an energetic collider was working anywhere in the world. And then the Higgs was sought after. People thought this is the God particle. We'll have a black hole and then a bomb, and then Switzerland will explode, and then the world will explode. I remember that well. The hysteria in the newspapers was unbearable.
You know what I think? We have a fantasy like this. You know how we'll do it, and I mean Y2K. Higgs boson, or like the Large Hadron 2012. Now climate change. We have this death drive about ourselves where we like the fact that everything might end. It is this very sadistic, very end time pleasure that it gives us. This relaxed, I don't want to do anything anymore. I don't know why, but every 5 years there is a end of time memory that comes up, right?
I might agree on that. I wouldn't go as far as to compare between the hysteria of the Higgs boson to concerns about climate change.
I'm not saying, of course not. Climate change is super real. I'm not one of the deniers of climate change.
Of course.
Right.
But yes, the hysteria with the Higgs boson discovery was really fantastic.
Right.
I mean, I couldn't believe, they said the God particle, the world is going to explode. The physicist, I was hearing people from news outlets criticizing physicists at CERN that have been working in the field for 30, 40 years. They're saying that they don't know what they're doing and it's too dangerous and so on. So this is all craziness. That's why I didn't like this God particle
gibberish.
Right. Let's leave God out of it, and let's just describe what we understand, which is a particle, immensely important, works through a special mechanism called spontaneous symmetry breaking, and it generates mass to other particles.
You know what I like about you is that your English is just such a nice mixture of the British accent and the Israeli accent.
Well, thank you. I guess anyone's figure of speech, in some sense.
Oh no, I'm half American now. By
tells
that
a story about
where they've
been, and what they have experienced. I guess every voice tells a story, if you will.
So, what are we expecting to find next with the LHC?
Right. So there are many endeavors in the LHC. When you're asking what we're trying to find next, you're asking about theories. Why am I saying that? Because if you were to go today to CERN, to the LHC, you'll see lots of work going on, construction, craziness, lots of people, and everyone's out super busy, and because this is a long shutdown of upgrading the detector to a high luminosity detector to be able to produce more information and describe the world better. But this is what goes on if you will, on the engineering side, on the purely experimental side, to improve the apparatus. But this is not what we're trying to find. What we're trying to find is the theory behind it. The theory is divided to main subjects which are popular. One of them, of course, is dark matter. Dark matter is one of the most important directions of investigations for different experiments in CERN.
Right.
We think that we have something that is responsible for more than maybe 85% of matter in the universe.
Right.
And we don't know
We have
anything
no idea, right?
about that something.
No idea.
But
And this 85% is comprised of both dark matter and energy? Because I think it's...
Well, dark energy is something a bit different, and even the name dark energy is not something that is agreed upon. Dark matter, on the other hand, is, well, dark matter might not be one thing, right? It might not be one particle which you say, this has, the energy of 20 GeV or 10 MeV, or doesn't matter, and this particle is dark matter. That's it. That's everything. Dark matter can be a range of particles that comprise the matter that we don't know to describe in the universe.
Right.
So yes, it must.
So 85% of the matter in the universe is dark matter.
Might well be.
Right. Okay. Wow.
Well, we can say that 85% of the universe, matter in the universe, we don't know how to describe it, and this more or less comprises around 25% of what we call the energy density of the universe.
So, because it's funny in the sense that, when you see all those pictures, and I'm speaking as a layman because I am a bloody layman at this, when you see all those pictures of the universe, all the stars combined, all the galaxies, all of that combined is probably just 15% of the universe, and that's all we understand from a distance.
Well,
is that an accurate statement to make?
Well, nearly. Let me just you can ask why. We can ask why do we care about dark matter? Why consider it at all? What made us concerned? Maybe that's everything. Maybe we see everything, and maybe we know everything.
Right.
So the strong evidence for dark matter comes from what we call gravitational lensing and calculations that predict by classical mechanics and other cosmological calculational techniques that galaxies would sort of spring off each other and scatter off to different locations. However, through through gravitational lensing, you see the opposite. You see that galaxies often orbit a center, although the center is empty in a sense. You try to look at the center, you see there's no mass, there's no star. So
we don't even see mass?
No.
Oh.
Why are they orbiting?
But
what are they orbiting around?
Isn't orbiting a function of gravity? Right, and so the theory of general relativity that Einstein he equated mass and gravity, didn't he?
Well,
in some sense,
yes. Yeah. But this is another story. But yes, indeed. I mean, you look at something, you say, we have mass at x, y, z equals 0. We have another mass at x, y, z equals 1, and then this has initial velocity of whatever. How will it orbit? Will it escape the gravitational field or not? But yes, this is classical mechanics, first year mechanics, that's fine.
Right.
So of course
first year mechanics.
Of course, no, really. And then we have more cosmological techniques of describing what should go on. If you look at these calculations, they say that the galaxies would sort of spring off each other and travel on their own path.
Right.
Although when you look through gravitational lensing, you see that orbit.
Right.
And this is the strongest evidence for dark matter. Of course, you also have evidence for dark matter through something else, which is called CMB
cosmic microwave background.
Exactly, the cosmic microwave background observation. This is analyzed through very advanced computational methods, and indeed traces of dark matter may well be attributed to what we see in the CMB.
Right.
Of course, there are others as well, and there are good models of their interactions with the baryons, which are composite particles as well of odd number of quarks. But again, this is all phenomenology. We know nothing. We are completely ignorant of
what dark matter
is, and it's very substantial because it's here and it's there,
and it's more than anything else.
And it's more, exactly. Yeah. So a lot of experiments in CERN will be devoted to finding dark matter.
Here is what I want. I want to jump to the meatier, juicier quantum places, but I still want to get this one little bit clear on this chapter of dark matter. To my understanding, which is again the most stupidest person you've met in this field.
No, the exact opposite.
The Einstein said that mass and gravity are sort of related.
Okay.
Right? So if we find no mass with this dark matter, how is it that it exerts a gravitational force to pull galaxies into orbit? What is happening? Is there a differential force that does that? What is up?
Maybe our methods of detecting mass
are incorrect.
Are not sophisticated enough.
Whoa.
We don't know, right? How do we measure mass, right?
Right.
How do we measure mass? This is not as simple as
question,
you would.
Yeah.
It's not like you go to the airport, you think your luggage is too heavy above the threshold to put it on the weight, the
you try
meter,
to charm
and
the
you
air
see,
hostess.
well, what's going on exactly. So, dark matter candidates have theoretical masses, but we have not found them yet. So, this is very unclear.
Wow.
Even things that had been thought for the large part of the 20th century to be massless are not massless. These are neutrinos, for example. Neutrinos are the lightest non-massless particles we know in the Standard Model. However, the Standard Model itself predicts that neutrinos are massless. A slight extension to the Standard Model by usage of quantum mechanics methods predicts that neutrinos are massive indeed. So this is a bit different. Yeah.
But you know what really messes with my head is the fact. So when we were talking about earlier as well, and you mentioned neutrinos, and I have heard of quarks before, and I've heard of the Standard Model before, and what I was taught in the name of physics was primarily limited to electrons, protons, neutrons, for that matter, or the classical end of stuff. Very, very, what now seems to be extremely preliminary. And since my introduction to the quantum field of analysis, the quantum mechanical realm, it seems almost like I was betrayed. As to, if you were to give me education in a particular field, why not go the distance? I don't care if it's tough, but go the distance and tell me what it really is. We are examining the nature of reality itself. Why do you think do we settle with the classical notion when the quantum notion's been around for over 100 years now?
Sorry, where are we settling with the classical notion?
No, in high schools and like in
oh right,
you know,
you're asking why in high school we don't teach quantum
for sure,
mechanics.
Yeah. Why don't we begin with quantum? Because if that is the essence of it, why is it that classical is still being examined?
This is simple to answer. Classical mechanics works most of the time in your life, right? So if you think about your day-to-day life, we mentioned a few minutes ago, the weight of your luggage going to the airport. So let's look at this whole process.
Right.
You go to the airport, you use your car. You measure your luggage weight. Then you have aeronautic technology when the plane flies off and lands. This can be all traced to classical mechanics, right? You don't need any quantum mechanics for everything you do in your day-to-day life. Right. Of course, I'm not referring to quantum technologies, which are very important to semiconductors and superconductors and so on. Right. But let's leave that aside. Generally, in your life, you don't see quantum mechanics and you don't feel it. Right. Your innate tendency of thinking about physics is classical. This is known. This might not be good, but it is the reality. We can, of course, discuss whether it's better to teach quantum mechanics first, but even quantum mechanics is, there are many methods of teaching quantum mechanics. Of course, there are many methods of teaching classical mechanics, but I would say that quantum mechanics is much newer, and hence you have the approaches are even more varied than classical mechanics, which is sort of textbook, very textbook stuff. Quantum mechanics as well is textbook stuff,
right?
Although the approaches are much newer, 20th century approaches. Right. Classical mechanics is Newtonian mechanics, right? Classical mechanics is described more or less fully by Newton, third laws.
Right, three laws, right.
Three laws of
conservation, entropy.
No, entropy is related to thermodynamics.
Okay, cool.
But three laws which...
Oh, for sure. Yes, I remember now.
You have the first law. The high school law. Exactly. If you don't touch anything... if a particle is in zero acceleration, it will stay in the same velocity. And of course, the second law, F
is equal to ma squared.
Not ma squared. You're mixing up with E equals mc squared, which is something else. But you have F equals ma, and the third law is, of course, every action
has an equal and opposite reaction.
Yes, in a sense.
I got the third one right.
So this is described. This works well in high school or in kindergarten. You don't think about quantum mechanics because you wouldn't think about it. There is no trace in your life, not even one, that can say, "Oh, this looks like quantum."
Right. So it seems like classical is functional reality in some sense, right? It's not reality in the most accurate, truthful sense, but it's functional because that's how we perceive the world. And I wonder at that, because if I think quantum is a leap in the sense that we were probably for the first time able to move beyond what is physically perceivable by us and just rely on pure mathematics as a divine algorithm to understand the nature of reality. How did we understand in the first place that this is not real, there is something that is being hidden because of our sense limitation? Did you find my question?
You mean how was quantum mechanics first
found? Yeah, like how did we even dream of something so absurd?
Well, right. I think I should mention two famous experiments. One experiment is related to the wave particle duality of light.
Right.
So it's the double slit experiment. The double slit experiment, when it was conducted early 20th century, you had two slits. You had light goes through the slits, and then you saw fringes. Now you don't. Okay, why would you see fringes at all if all the light would be scattered around?
Right.
What they understood when they saw the fringes of light, it seemed as if light can be described as a particle as well.
Right.
Not only as a wave that would splash out throughout the wall, but rather quantized in specific locations on the wall that can be separated. Those locations, the spacing can be quite easily related to the wavelength and frequency of the light through what some would say a quantum mechanical calculation. And this, of course, exemplifies the nature of light as a dual being. If you really go deep into the notion of what is quantum mechanics. Well, quantum mechanics has a very diverse history, right? You can relate this to what's called as the Vienna interpretation and what Einstein thought about it and so on. But I would say that if you really want to understand what's the difference between what is quantum and what is classical, you ought to discuss the EPR paradox. EPR is an abbreviation acronym for Einstein, Podolsky, Rosen. Einstein, of course, everyone knows. Podolsky was a Russian Jewish scientist working in the US as well, I think. And Rosen was, of course, Nathan Rosen was American Israeli philosopher, science, and a physicist.
Yeah.
Yes, working in MIT and Technion as well, and other places. And they thought that quantum mechanics is not a real thing. Einstein famously said, God does not play dice. And EPR wrote a paper saying that, well, more or less, if I can recall it correctly, that every local realist theory should adhere to causality. This is a bit, it's a good definition if you know what everything means, because it's concise. But if you break it up, you have to understand that, well, local means that it doesn't violate special relativity, so nothing travels faster than light. Realist means that if you know all the information about the system, you can predict everything, essentially.
Laplace's beast.
Exactly. So if you measure the system, you know the system.
Right.
And if that's true, yes, it has to agree with causality. So nothing influences something in the past. And so on. So they wrote that, and a few years later, John Bell, Irish physicist, I think, Irish-American.
John Bell?
Yes. Had a paper about the Bell inequality, where he he produced a very good mathematical mechanism of differentiating between what is quantum and what is classical. And indeed, this has been tested several times with specific experiments which tested what you might have heard of as entanglement. So through experiments in different locations around the world, lately most notably I would say an experiment in Delft in the Netherlands, in Holland, that tested the figure of merit of quantum mechanics and classical mechanics, the border. So whether you can predict what will happen or you can't, and everything is quantum and there's a probability of what will happen. Entanglement is something a bit different, but it's a good way of separating something quantum to something classical.
Right. So how does the EPR paradox get settled? So if the
Yes, so this is a good question. The EPR paradox
what they're referring to in the statement that they make, that the local realist must adhere to causality, is a classical notion, if I'm not wrong, right? So they're saying that this has to be the case, therefore classical is reality. And then Einstein says God does not play dice, means there is no probability of an electron being in two places, if I'm correctly getting it. So how does this get resolved, the EPR paradox?
Well, quantum mechanics works. Quantum mechanics has been tested.
How did we come up with it? Like, who? I think Schrodinger came up with it.
Schrodinger came up with a very, very important and famous equation which has two forms, which is called the Schrodinger equation. The two forms are the time-dependent and the time-independent Schrodinger's equation. The Schrodinger equation is a wave equation that describes a wave function as a function. Well, in the famous time-dependent Schrodinger's equation (TDSE), it describes how a wave function, and we can talk a bit later what's a wave function exactly, but how does a wave function behave as a function of time and location. So the Schrodinger's equation is immensely important when you try to know everything you want to know about a system and how to describe it with a wave function. The solution to the Schrodinger's equation is the wave function. The wave function describes everything you want to know in a quantum mechanical system. And if you like, I can just say that a wave function, you can say, is a linear superposition of yes, I shouldn't be too technical.
No, go ahead. Because
but essentially, it's a bunch of states. We call them eigenstates. Self-states, okay. Yes.
Right.
Of a system or of a particle. And the system can be in one of these states depending on the probability or the amplitude of each state. The wave function is all of these summed up and
to give one answer.
To give different possible answers depending on what it collapses to. This is quantum mechanics, right? So let's say we have a particle and we think about its energy eigenstates. Okay, so in quantum mechanics you would say, let's say it has 3. Let's say the probability for each one is 1/3, and then we say we make a measurement or an observation, and then we say, okay, what is the energy of the particle? This depends on the wave this depends on the eigenstates to which the wave function collapsed to upon making a measurement. And then the energy of the particle is the associated eigenvalue of the eigenstate we are in. This is different than if I were to tell you, you have a mass, the mass is moving in 100 kilometers per hour. Let's wait 2 hours.
Where is it going to be?
Where is it going to be? Yeah. What is its energy? This is nothing to do with quantum mechanics. This is classical, right? But if I were to ask, I tell you, you have an electron. The electron can be in one of 10 eigenstates. You don't know anything about the system. You just know the wave function. Take a measurement. Tell me what you get. Surprise, surprise! You got 1 out of 10 eigenstates. It is a surprise because you didn't know in advance which eigenstate it was going to fall into. Right. So this is the opposite of the example of the mass moving in constant velocity or even not constant velocity.
Right. So here is the layman's understanding, or at least a stupid man's understanding of quantum. What I have been educated with, as far as the books or the blogs or the podcasts I've listened to on this subject, is that quantum derails the notion of classical physics because it adds a probability of an electron being in one of 2 places, or sometimes even 2 places at once, which is absolutely opposite to the classical notion as we just discussed. How much of that is true? What am I understanding it correct? The fact that it is only upon observation that we can place an electron or a particle in space. Up until then, it could be anywhere. Isn't that the Schrodinger's experiment?
Well, Schrodinger did not conduct experiment.
The Schrodinger's cat thought experiment that he has.
Well, if you refer to Schrodinger's cat. So the Schrodinger's cat is very famous and very popular. Of course, you put in a cat in a box, you open the box, it can be alive, it can be dead, we don't know. Of course, we
don't know until we open the box. It can be both alive and dead.
Yes, indeed.
That's how I have understood.
Yes, this is the thought experiment.
Right.
You refer to the location of a particle. I had referred to
the states,
the energy of the particle. So it's not only energy or location, it can be momentum, and it can be spin, it can be different things. So in a sense, every property is probabilistic in quantum mechanics. So classical mechanics and even statistical mechanics, even in statistical mechanics, you know for sure what's the statistical state you find the system in. It's just a method of describing the whole system rather than one particle, as in high energy physics.
Right.
So quantum mechanics is very different, because quantum mechanics says that you can have all the information about a system, all the information completely, and then still make a measurement and have a surprise, because there's a probability to be in one state.
Right.
Not only location, it can be momentum, and it can be energy, it can be different states. So as I said before, every eigenstate has a corresponding eigenvalue. There is something immensely important, which is also very quantum, which refers to the Heisenberg uncertainty principle.
I sort of heard of that. What
yes.
was that? Yeah.
Okay, so for example, this is the limit of our ability to know two things at once about the same system. Let's start with a classical example. If you know the location of that moving mass or moving car, and you told me its location, and then I told you, okay, thanks, got it. Now tell me its momentum. And you'll say, fine, no problem. You will take its velocity, you'll times it by its mass, and you'll tell me the result. This is the momentum. In quantum mechanics, we have something rather different, which is called the Heisenberg uncertainty principle, which means that there is a limit to the accuracy in which you can know one property versus the other. So if you want to know the particle's location to infinite accuracy, you can have its momentum also. However, its momentum will be given to you to a very high inaccuracy. On the other hand, and vice versa. On the other hand, if you wanted to know its momentum to high accuracy, and then also its position, its position will be very inaccurate. Similarly, with other things like energy and time. So if you want to know where is it in time, and what's its energy, you can know one of them, but you can't know both to a good accuracy. There is a limit to the accuracy. That limit is related to Planck's constant. So Max Planck. Yes, Max Planck was a German physicist. Perhaps you can say the founder of quantum mechanics, although he would be disapproval of that. He didn't like those attributes, although
what a humble man.
Yes, very humble. Planck's radiation quantizes the radiation of a black body. There's a very famous equation that the energy of a black body is equal to a constant times the frequency of the emission of the black body radiation. E equals h nu, or if you like it, E equals h bar omega, but it doesn't matter. So this constant, which is related to the quantization of radiation of everything, is related mathematically to the commutation of operators. So let me just quickly break that down. Operators in quantum mechanics generate eigenvalue. So the method of analyzing quantum mechanics mathematically is linear algebra often. So operators are described by matrices, and then
we got into this when we were speaking earlier.
Yes,
as well.
indeed.
Right,
Yes, we mentioned it. And then operators are often described by matrices, and those matrices operate on what we talked about earlier, eigenstates.
Right.
And
that
then
forms the observation concept.
Exactly. That forms the observation, a value, which is called the eigenvalue.
Right.
And that eigenvalue is the property that we want to analyze.
Right.
Now, this operator is what we plug in the Heisenberg uncertainty principal equation to know the commutation of it with another operator. And the commutation result is the limit of the accuracy
to which we can predict the second state.
Yes, exactly.
Right.
Or yes,
I figured it out.
Depends which state you call the second, which you call the first.
Right.
What's very interesting about this also, I will just mention this and we can move on if you like,
Right.
is that inside this equation, apart from having a constant, you have I. I is the negative, is the root of -1, which is unphysical.
Right. It's a complex imaginary number.
It's an imaginary number.
Right.
Well, it's just I. Why is it there?
Why?
I don't know. No one knows.
No one knows.
No. Why? So we have the famous equation is take the position and the momentum. X is the position operator. X.
Right.
X hat. We
Right.
say X hat. We have a hat above it.
Right.
And take P. P hat. We have a hat above it. You put it in the commutator,
Right.
so meaning that x times p minus p times x.
Right. Should be 0.
In the classical world, why not have it 0?
Right.
What's the difference of multiplying 6 times 4
into 4 times 6
or 4 times 6? Right. There's no difference.
Right.
Okay. However, in linear algebra and especially in quantum mechanics, with operator, there is a significant difference, and of course in regular linear algebra,
there is a difference.
Matrices are generally not necessarily commutative.
Right.
Okay.
Right. I is not equal to J. Is that's transposability?
Yes, that's a transposability.
Right.
What I meant that if you have M1, matrix 1, and M2 is the second matrix, M1 times M2
is not
need
equal to
not necessarily be equal
M2
to M2 times M1.
Right.
And this is important, very important. If the operators commute, it means that the operators share eigenstates.
Oh my gosh!
Yes.
Yep. This gets
crazy.
This gets fucking crazy. You know, it's for me, it's like a dark room, and there is some light once in a while, and I'm like, oh yeah, I can hold on to that. Like that piece of information makes sense to me.
This you can have that for 2 minutes.
Yeah,
that's it.
Yeah, and then
you have something new.
Quantum's been so elusive because. So here is a notion. And we did not discuss this the last time we were talking about the subject, but I read a paper by an evolutionary scientist named David D. Hoffman. I'm not sure I think it's U Michigan or U Wisconsin, one of these schools. And he speaks about the distinction between what we observe, which is the classical physics mechanism, and which is the quantum physics mechanism, as our perceptions being an evolutionary schema, something that we've developed in our evolution to be able to perceive, which is an approximation, which is fit enough for us to survive, but not quite the reality. And why I posit this is because it sort of changes the dynamic of my interaction with reality. I no longer am in a place where I would trust my senses for absolute truth. And it has philosophical implications, it has all sorts of implications for me on the other end of stuff. But from a physicist's point of view, what do you think about the distinction between the classical and the quantum being that of an evolutionary approximation?
Well, this is a very profound question. I'm not an expert in evolutionary science.
For sure, yeah.
Nor in biology. I can comment maybe that of course we evolve as people very rapidly, especially in the last century. Of course, the evolution is not linear, right? So the difference between humanity's intelligence in, let's say, the year 1200 to the year 1300, although it's 100 years difference, is not comparable to
it's
the
like
difference.
Moore's law.
Exactly.
It's like Moore's
Yes,
law. I
exactly,
believe that because we
exactly.
bounce off
Exactly.
our extended phenotypes
Of course.
for our intelligence standards, right?
Of course. So if you, for example, if you're a fan of Ray Kurzweil,
Oh my gosh.
I am.
Right.
So he thinks that it's not exponential, it's super exponential, right? So the difference between yesterday and today is not similar to
It's not
the
2 and
difference
4.
between tomorrow and the day after tomorrow at all.
Right.
Similarly, we are very much different from 1900 humanity than the comparable 1300 to 1200.
Right.
So
right.
our perception of reality will be more and more objective. When I say objective, I mean less limited by our human limitations,
Right, whatever that might be.
and abilities, and more scientific.
Right.
As time evolves, we'll be able to understand what goes on around us better. Of course, it's not only what goes around us, it's also what goes on inside of us.
Right. That's where Ray Kurzweil really kicks into me.
Of course, some people, and I think that is very valid, think that, of course, as we understand more about fundamental physics, we will have more landscape for neuroscience to dig into. So if you think about Roger Penrose, he thinks that the way that the brain function maybe in some future can be attributed to quantum mechanics or other physical theories.
Right.
So this is
It gets excessively complex when biology and quantum.
So
get into
exactly.
that.
So in terms of evolutionary science and evolution in general, of course, we are today much fitter to test physics and test nature, unlike the state we were in hundreds of years ago.
Right.
So of course, science is the drive and maybe in a sense the figure of merit of the state of humanity,
Right.
if you will.
Right. So let me take it to another scientist, another person that I've been reading up on, and his name's John Wheeler. John Wheeler's,
Right.
I'm sure John Wheeler's more your person than, because I study evolutionary sciences.
Okay.
He says that information is the fundamental unit of the universe, not particles.
Yeah.
The fuck does that mean?
Well, again, I've heard that before. I
Right.
think you've mentioned it to me. There is also a famous phrase, I think, by him, it from bit.
Yeah, it from bit. Yep, information technology to quantum
it
mechanics.
from bit.
Yeah.
So
That's where he mentions this. That's
yes,
the paper.
It is what we have, and bit is the information.
Right.
This is often related to entropy. So entropy is a good description that is available through physics, through thermodynamics and statistical mechanics
Right.
of information in a system. So entropy is sometimes described by the amount of disorder in a system. Often in statistical mechanics, in thermodynamics, you have different properties, have a bit of a sketchy definitions. For example, how do you define temperature? Is it heat? Is it energy? Is it what? So similarly, entropy is often described as the amount of disorder in a system. If you look at the second law of thermodynamics, says that entropy in a system must increase all the time. Means that in some sense, well, it's very hard for me to relate that to it from bit and information, but you can say that entropy, in a sense, can measure how much information is given, can be gained from a system, and how it is related to statistical systems.
Right.
And of course, it plays an important role in the analysis of black holes by Hawking and others, relating to the information that can be gained from black hole radiation and whether the information is conserved or not. Right. But yes, indeed, in different aspects of physics, information serves as the figure of merit for what we can trace of the system.
Not particles.
Well, it's too general. Hopefully, we can relate information to specific particles in the near future. But I think that's quite far off now.
Right.
I'm sure your viewers will be interested in reading a book I can recommend. It's The Black Hole War. Leonard Susskind, a professor in Stanford University, about his about his debate with the late Stephen Hawking about information. So I'm not a big expert on that, but information is a recurring theme in that book, whether information that that entered a black hole can be gained through the Hawking radiation after. So, yes, but again, this is all I can comment. It from bit is very. It's like a thought experiment, and it's more maybe of a philosophy of science question, a bit general and not particular.
See, that's where I like myself, in the general.
Right.
But I feel, and correct me if I'm wrong, because I want to jump on a few other topics before I begin to close. I feel like what Wheeler was trying to get at was that the Laplace's beast, the prediction of everything if particle and its properties are known in a system, there is a transformation that we need in our thought towards having information as the fundamental unit of understanding a system, not particles as such. That's what I got from
yes. That's
sort of what he's getting.
A good description. Laplace. I think Laplace never called it demon by itself, by himself.
Right.
But yes, demons as thought experiments are also a recurring pattern in physics. You have Maxwell demon says something else about entropy and thermodynamics. Wow. And of course you have Laplace's demon. And Laplace's demon it's an old notion. So I think in the first part of our discussion today, we referred to quantum mechanics and classical mechanics, and whether when you know all the information about the system, can you predict what will happen with it? So the answer is no. Well, no, because quantum mechanics works, and so no. But you can have a wave function, which is a probability density function of a system, and you can describe accurately what is the probability of obtaining of being in an eigenstate.
Right. So here is where I want to transition into this whole this probabilistic notion. Sure. Right. So the idea that I got is that if you observe, the spin of an electron, if you observe it under electromagnetic conditions, it could have spun up or spun down. Like the direction of the spin is constant, but it could have been up or down. And then there is the notion of action at a distance, spooky action at a distance, possibility of observing particles in two places. What is happening here?
Okay, so spooky action at the distance, again, a recurring pattern. This is attributed to different topics in physics, sometimes even to electromagnetism and the way the electromagnetic field works at a distance. But in terms of quantum mechanics, this relates to entanglement. Entanglement refers to the notion that two particles can, in some sense, communicate with each other, although they can't. So they can transfer information between them theoretically, or just by traces of evidence, although no channel of information
not in each other's field.
They're not close to each other. They are in black boxes, but still, when you measure the spin of one,
it has something to do with the spin of the atom.
Yes.
And we don't know why.
Well, we attribute it to quantum entanglement.
Uh-huh.
I mentioned earlier the experiment in Amsterdam.
Right.
In Delft.
Right.
In Holland,
Uh-huh.
when they tested it quite well. So, spooky action at a distance relates to Bell's inequality,
Mm-hmm.
and whether particles that are far off each other, that had something in common earlier,
Right.
like a conservation of spin,
Right.
which is a form of angular momentum,
Right.
are related or not to each
Uh-huh.
other when sort of boosted to different corners of the universe.
Wow.
So if entanglement works,
Uh-huh.
it means that without having a physical channel of communication,
Uh-huh.
we can still maybe channel information
From one particle to
through
the other.
entanglement from
Uh-huh.
one corner to the other corner of the universe.
What the fuck?
This is
Right.
crazy.
That's why it's spooky. That's
It
exactly
is.
why it's
It
spooky.
is.
And it's different from action at a distance?
No, this is spooky action at a distance.
Uh-huh.
I think this phrase refers to that in quantum mechanics.
Right. And action at a distance is similar, but spooky action at a distance is this particular. Or are these the same concepts?
It's the same thing.
It's the same thing. Okay.
Again, I think often that's why I like to be specific about it, because often when you think about popular science, or maybe not popular science, just popularizing science, you find yourself often involved in what each popular definition means rather than what we know.
Right.
So why is it called a God particle?
Uh-huh.
Why is it spooky action at a distance? Why is it called a demon? This is popularizing science.
Right.
These are thought.
It's packaging science.
Yes.
Marketing
yes.
science.
Yeah,
Right.
exactly. These are thought experiments. So it's in physics when we are trying to be useful and practical.
Right.
We think we just name the things as we know how to relate to them. Operators, particles, energies.
But then y'all
Momentum.
are boring, bro. You need to be more.
Yes,
You
yes,
get that, right?
I understand.
As a function of science, you have to be, for the functionality of it,
Yeah.
you have to be very A to B.
Yeah.
And then the people outside, they're sick of watching Donald Trump do all these crazy antics.
Right.
They need that fun.
Right.
So I get that. But
Yeah.
now, how is it that there is a possibility of observing the same thing in two places? Like, what is this?
Okay.
Yeah. How's
Well,
that happening in quantum?
it's not observed in two places. It's observed in one of those two places, but you cannot know
Which one?
And this is
Fucks
simply
with mad.
well. At this stage of our discussion, I can quickly attribute this to quantum mechanics.
Right.
Two eigenstates,
Uh-huh.
two position eigenstates.
Right.
You make a measurement,
Uh-huh.
and you're in one of the two,
Right.
and that's it.
Right. And the measurement is the observation. The observation is the operator's interaction with the eigenstate.
Well, observation in
Uh-huh.
quantum mechanics means a collapse of the
Uh-huh.
wave function.
Uh-huh.
The wave function, we already
Went into,
we've
yes.
been through
This is
that.
the masterclass in physics.
We've been what's an eigenstate.
Right.
So you have an eigen. You have a wave function
Uh-huh.
equals a sum of eigenstates.
Right.
This describes a particle. The particle can be in point A, can be in point B, can be in point C, can be in point 100, doesn't
Right.
matter. You make a measurement, and then its wave function collapses to an eigenstate, and that's it.
Right.
And that's then it is in the eigenstate. So, but theoretically, potentially, it could have been in a different eigenstate, right? Yeah, because there's a probability to anything. Even right, if you go to the vending machine, you don't know. Maybe you don't know what you're going to get. You might not know what's in there. So
Right.
there's a probability for
Sure,
everything.
sure.
Right.
I follow.
Although what's different about you and the vending machine and a particle, that we can be certain that if we had all the information before we went to the vending machine
We will
about
get
what's in there, what you like,
Right.
and maybe how much it costs,
And if I have the money and
We-
all those it's.
we can have 100% prediction of the result of your choice of drink.
Right.
Right.
But with quantum,
In quantum mechanics,
it
no.
has to be measured.
Yes.
To know. Up until, even if you have all the information, you don't know until you measure.
Yes.
Right? I get
Yes.
that right?
Yes.
Hell yes.
Sure.
One more stage.
Brilliant.
How tired are you?
I'm as tired as you will tell me to be.
Okay, so I have about a few more questions.
Sure,
At
go
least
ahead.
one question related to quantum, and
That's
then I
fine.
want to get to general physics as a whole towards
Okay.
the closing of it.
Sure.
What was Hugh Everett talking about when he spoke of many worlds? What the hell is that?
Who?
Hugh Everett?
Yes.
Right. What was
Okay.
what's the many world conception in quantum mechanics?
Yes, sorry. Many worlds in one word is often related to multiverse. So universe, multiverse.
Right.
Right. You have a vowel, constant. You
Right. yes.
bank up the word.
Yes,
So multiverse is a notion which is very natural. When you accept quantum mechanics, the next step is accept multiverse, right? So if everything can be in different places, and have different energies and different momenta and different spin, why not think of the universe to be different completely depending on its eigenstate?
Right.
But again, I should be very careful about this because there's often misconceptions about quantum mechanics. There's
The woo-woo.
Yeah, sorry.
The woo-woo gets
The
attached.
woo-woo is crazy. Yes,
Right.
there was a film a few years ago. I think it was called Blip, or What the Blip
Oh,
is.
who was the guy? They totally gerrymandered his statements to make that case on that film.
Yeah.
So, have you heard the story afterwards?
No,
What happened?
no.
So the guy in the film, I don't remember who.
Yeah.
He kept in his document whatever he said was XYZ ABC. He was trying to be as rational as he can about the entire notion of quantum physics, but the producers and the directors of the film cut it out to make their narrative, the woo-woo. So they totally manipulated his statements to make a case for this woo-woo kind of stuff with quantum mechanics.
So yes, we should be careful about this.
Right.
Even the multiverse, it's often very seductive
Right.
to think about multiverse, and we don't know what we see, and everything is upside down, and everything is not real, and we're not here. This is not an interview. This is an eigenstate of something. That's fine. That's fine. We can have fun talking about this, but this is just mumbling, right? It's mumbo jumbo. It's nothing.
Right.
This movie was poison to
The
people.
physics community.
Actually not, because the physics community
knows what's
was
up.
immune.
Right.
They were immune beforehand. They were fine. It was poison to the general population because it made them think wrong ideas about quantum mechanics. Right? It made them think that if they look across the door, the furniture might be in an eigenstate, and if they look again, the couch will be above the window, and the floor would be upside down, right? And the television would be in the pan frying. So no, okay. We have classical mechanics, we have quantum mechanics, and we have to understand where is the boundary between them to be very specific about it.
Right.
The Bell inequality is immensely important because it gives eventually a simple mathematical figure of merit to differentiate between what is classical and what is quantum mechanical. So multiverse is interesting for the very clever people who do theoretical physics.
Right.
I wish all the best, and perhaps
that is the truth.
That is the truth, but it won't make any difference practically, neither in our lives nor in what we search for
with physics as a whole.
With high energy experimental physics in the next several years in front of us.
Right.
We're searching for new particles, new forces perhaps,
right?
Maybe dark matter, maybe leptoquarks, maybe unifications of forces into symmetry gauge groups. That's fine. This is specific, it's practical, it's hopefully manageable.
Right. So what
multiverse is nice.
Right, it's very pretty.
We have nothing to do with it now.
Right.
Me and you.
Right, of course. It's not functional. But I think what Everett was saying was that it is upon observation that both the possibilities of an electron's position are realized, and in that moment, the world splits into two, and you are part of the one, and there is another Prakhar and another Roy and another Tomer that continues on the other end. It's an infinite loop, and it's a constantly splitting universe. That was like the theoretical model he gave, if I'm not wrong.
Well, I'm sure that
that is the case.
A theoretical model would be very technical, very mathematical, hard to understand, and not popular by the popular community.
Okay, I see what you mean.
The popular community, and that's fine. I mean, this is fine. I don't expect anyone that is not directly involved with physics to read a paper that is meant for physicists. I think it's important to popularize science, but in order to do so, things can be simplified, but they don't need to be, laughable.
Right.
They don't need to
caricature.
Exactly.
Right.
We don't need to draw a caricature of science.
Right. Because that's miscommunication.
In order to make it popular.
Right.
It's good enough. And it's superb and divine enough the way it is. We don't need to make fussiness about it. And then
that's something only a scientist will say.
People will like it.
Right.
People will like it.
Okay, so towards the close of it, there's just two questions that I need to get out here.
Sure.
One of them is, where are we currently at with physics? What is our current position? And then two, what are we focusing on next? As a community as a whole, as humanity as a whole, where are we at and what are we orienting ourselves towards in the next few years to come?
Okay, this is a very big question, of course.
Let's condense it. It's been an hour, 15 minutes already.
Sure.
Right.
Well, we can, of course, divide this up to different aspects of physics. I should say very quickly that one of the big things that is unrelated to what I do is quantum information, quantum computing. This is now buzz, but it is real buzz, and it's important. We had this leak about the quantum computing achievement that was achieved by John Martinis and from University of California with Google.
Right.
And might be published soon in Nature, unless I'm not fully informed that maybe it has been already. This will change the way the world works. Right. Everything will change. The speed is a crucial factor in everyone's life. Internet is obviously like air to breathe for nearly everyone. It will change the third world very quickly again. It has already done so. So quantum information, quantum computing, one of the big things in physics generally, and this is true for quantum optics in some sense. It's true for solid state physics and other fields as well. In high energy physics experimentally at least is going for dark matter at full speed. We have good theories, good models that have got dark matter candidates in them. We are looking for leptoquarks to relate between different forces in the Standard Model. And of course, the theoretical high energy physicists are trying to unify. We're looking for unifications, right? In the 20th century, physics has progressed substantially through unifications. Okay, we've unified. Well,
the Standard Model.
The Standard Model is a unification in some sense of special relativity.
Right.
Traces back to 1905 with quantum mechanics through quantum field theory. Now we want to unify that with gravity. So Einstein's theory of gravity, Einstein's theory of gravity, GR, general relativity, should be hopefully unified with all the rest. I don't know how. I don't know how. I don't know who. I don't know when. But
that's coming. That's on the agenda.
This is the substantial main hope for string theory. So quantum gravity is a substantial big thing as well.
Right.
And maybe string theory would be successful in that. There's a long way to see, but so far it has been the most successful out of many theories.
Right.
Yes, and of course, there has been a very popular model of supersymmetry, although less popular today. Some searches in high energy physics are still trying to find that. And of course, beyond the standard model physics is the the tone of the day, the theme of the day, the zeitgeist, if you will, in particle physics. All searches now focus on 90% or more of searches are focused on beyond the standard model physics. A good example is the discovery of the neutrino mass and oscillations.
Right.
But of course, dark matter would be a phenomenal achievement, and others will. People need to be very patient, very, very patient. The endeavors are huge, the risks are high, the effort are beyond description, and the Higgs, in some sense, if you look at it in retrospect, maybe came about too easily. It was too quick. It was so quick, right? It was like turning something on, finding the Higgs, one of the most important discoveries
of our time.
Our time. But and then since the Higgs, they said, "Oh, what else?" So it might take time, but we should, have patience. I think big things are happening in many fields, and we see physics all around us influencing the world.
Everything. Physics is the fundamental science, except mathematics is a little more fundamental than physics in my view.
Okay. In any sense, we need patience, and we need belief, and we need hope, and we need to understand what's important.
Right.
In physics, when it works, and it always works, we just have to apply it and understand what is going on, is beyond grasp of its positive influence on the world. And of course, we want to understand, as being humans, the nature, right? We want to understand what we are made of and what is around us, and what are the laws that govern the universe.
Right.
So we have to have patience, and we're going forward in many directions. We see traces again and again in our daily lives, and this is this is
where we're at.
Very very rare, and indeed awe-inspiring, if you will.
Right.
Yeah.
Right. I see that. This has been phenomenal, Roy. It has been.
Yes.
You've been one of the fondest people, my fondest guests. It's been such a pleasure interviewing you. You were so articulate, so eloquent, so descriptive. Thank you so much.
It was a pleasure. Thank you very much for inviting me. It was a pleasure.
Mine.
Thank you.
Thank you.